Hello, my name is Katherine Rauscher, and I'm the project manager for Michigan Technological University's Astro-Huskies. This is our proof of life video for the 2026 NASA Lunabotics Challenge. This year's rover is MOOSE, or Mobile Operations for Off-World Surface Excavation. First is our faculty advisor, Dr. Paul Van Sassante, helping the team to verify MOOSE's mass and dimensions.
We're here today to weigh the rover and measure the size of the rover, and so we're starting with weighing the rover. All right, so right now the scale is set to 0, it's tarred, and so now we can see, we're going to put the rover on the scale, and then we'll read off the weight from that. All right, nobody touching, no touching the ground. All right, so the weight is 61.7 kilograms. So that's the current weight of our rover MOOSE. All right, well, the next thing we're going to do is measure the dimensions of MOOSE, the MTU Astro-Husky rover, and we'll start off with the length first. This is in its storage position, and so we'll measure it from the front part, which is the point of the bucket, to the furthest rear point here, and our dimension is 55 and I guess 15/16 precise. For the length. All right, and next we'll go to the height. So the highest point is our stop button here. Make sure that we are level. Let's see if we got raise that side a little bit, a little more. There we go. Now we're level. And we'll measure the distance from the surface here to the bottom of our bar, and we are at 28.5 inches of height. And the remaining is the width of our vehicle. So the widest point are our bolts on the wheels. So we'll put our stands right here. And then the width from one side to the other is 29 inches and a quarter. 29.25 inch. So that would be the dimensions for our robot.
Next is Dr. Van Sassante verifying the size and functionality of MOOSE's emergency stop.
This is just a purchased e-stop, and as you can see here, it is 40 millimeters in diameter. The power all comes from one single battery over here, and all the power is routed through the e-stop. The only thing that's left powered after pushing the e-stop is the watt meter as required. And so we're going to demonstrate that now. As you can see right now, there is 0 power being drawn, and now we turn it on. And as you can see, there is power being drawn right now, and the e-stop, when I push it, all the power draw goes away, but this stays powered.
Next is one of our systems engineers, Royce, to demonstrate that we can effectively switch between the 2.4 and 5 gigahertz bands on our wireless access point.
So currently I am connected to the 5G network. I'm going to connect to the 2.4G network right now, which I am connected. I can demonstrate on my phone here that those are indeed 2.4 and 5G networks.
Because your phone is the router app, right? So.
Yep, my phone's the router app. So I have a 2.4G and a 5G named as shown here. And then if I want to turn off the 2.4G, super easy. I can just turn it off like so. And then that'll take a couple seconds to update. All right, on the phone app, that says that the 2.4 is off. So if I refresh that page, connection failed on the 2.4 that I was just connected to, as I would expect. Just make sure it updates properly that network is gone, and it is. So I'm now connected to the 5G, the 2.4 is off.
Finally, Here is Dr. Van Sasanta again, approving our footage of a representative competition cycle in Michigan Tech's regolith simulant chamber at the Planetary Surface Technology Development Lab.
The last part of this video is showing a live demonstration which was recorded last night, demonstrating a single cycle of operations, including excavation, traversal, and deposition. And so this shows all of these different things, and as faculty advisor, I approve this message.
Moose begins in its stowed position in our starting zone and is able to immediately deploy a 4-bar actuated bucket scoop to begin excavation operations. The bucket scoop operates as a surface skimming design, as opposed to a bucket ladder trenching design like the Astro-Huskies have used in previous years. Once full, the bucket is retracted into the dump position and approximately 10 kilograms of regolith simulant is deposited into the belted hopper. Because of this surface skimmer design, Moose requires a large amount of mobility and traction capability, which is achieved with a 4-wheel independent steering system. This allows us to use unique mobility modes such as double Ackerman, 0-point turn, and crab drive, as shown here, while Moose maneuvers to start a new excavation trench. To achieve this, each wheel has its own motor and linear actuator that interface with a custom steering knuckle design. The large, straight grousers on each wheel allow the rover to achieve more traction, especially when digging the bucket through densely compacted regolith simulant. To excavate these more densely compacted areas, the cutting edge of Moose's bucket scoop has custom machined teeth that break up the simulant so it can enter the bucket. These teeth have a modular design, so they are easily replaceable if damaged over time or upon impact with an obstacle such as a rock. Here, you can see the team prepare to make use of Moose's robust mobility to get out of some loose regolith that it sinks into during excavation. During competition, the team plans to take 8 excavation passes for a total of 80 kilograms of regolith simulant in our hopper. This will be achieved across 2 or 3 excavation trenches as determined by our operators based on the positioning of obstacles in the competition arena. After the hopper is full, we take a 9th excavation pass and hold an additional 10 kilograms of regolith in the bucket in its stowed position while we traverse to the construction zone, as shown here. This will give us a total of roughly 90 kilograms of regolith transported per duty cycle. Once appropriately aligned in the target berm volume within the construction zone, the team will activate the chain and sprocket-driven conveyor belt to deposit all of our excavated material. Now, you can see Moose activate the double Ackerman mobility mode to traverse back to the excavation end of our testing chamber. While all of this footage depicts the rover in a teleoperational state, the team has also been developing an autonomous approach throughout the year. At competition, the team plans to achieve both excavation and deposition autonomy. The team may also achieve traversal autonomy if development is completed within time. Thank you for watching our Proof of Life video for the 2026 NASA Lunabotics Challenge. Michigan Tech looks forward to meeting and competing with everyone else in Florida. Go Astro-Huskies!